Uh, okay, so we will wait some time until uh, students are joined to the lecture. So please pass the message to join the lecture. Hurry up. Students join using one device, please mention your index numbers. Otherwise, I cannot get your attendance. Okay, then let's start. So in the previous lecture, we covered about some of heat treatment process like handling, stress relief, normalizing, and tempering. So today we go deeper into heat treatment, especially hardening, quenching, and case hardening. Okay, so this is the today lecture content. So there's a simple introduction part, then the under the heat treatment process, we will discuss about the quenching, hardening, and case hardening. Okay, so under this lesson, you have to identify the right heat treatment route for a job and can we explain the trade-offs. If a part fails by wear, you may chase surface hardness. If it is cracks in service, you may need a different temper or a case hardening part that introduce beneficially compressive stress at the surface. Okay, so there's a simple introduction. Heat treating is the group of industrial, thermal, and metalworking processes used to alter the physical and sometimes chemical properties of a material. Okay, so heat treating is a control heating and cooling toolbox for changing properties. Sometimes we change phases, sometimes we relieve stress or modify surface chemistry, in welding or hot working, high temperatures can create coarse grain and locked-in stresses. Heat treatment let us repair and optimize. So it's keep a mental model. Temperature creates opportunities for atoms to move. Time lets changes complete, and cooling rate free maps temperature versus carbon content up to 6.67 for iron alloy. So it's map that tell us what structure iron has, that different temperature and carbon levels from poor iron up to cast iron composition. As we heat or cool, iron can exist as a ferrite or austenite or austenite iron or high temperature, it's a high temperature form, or combined with carbon to make cementite. So this material is very hard and brittle. Okay, the diagram is divided into regions showing where each phase is suitable. Single phase areas like pure austenitic or ferrite, and two-phase mixtures like austenite plus cementite. Okay. Uh, Okay, so knowing where your steel sits on this map lets you predict what happens during heating, holding, and cooling, and therefore the hardness, strength, and toughness you will get. Okay. Okay, so then there is the structure and strengthening by heat treatment. Okay, so think of austenite as the high temperature parent that we create on purpose so we can transform it into what we want. Its crystal is FCC, which has lots of slip system. FCC means face centered cubic. So it's ductile and can dissolve a lot more carbon than ferrite. We get it by heating steel above the critical temperature. Okay, so we hold long enough for the wool cross section to become uniform austenite. Okay, the matter of grain size is using fine austenite grains can produce finer products after transformation, and those products have better toughness. Okay. On cooling, austenites can go two ways. The first one is diffusion control, and the second one is uh, diffusionless control. Okay, so the diffusion control means use slow, medium cooling to ferrite plus perlite or bainite. Okay, then the diffusionless means fast quench to mertensinite. Okay, okay. The austenite is not our final strengthening stage. It is the starting canvas, and its composition and grain size set the ceiling for the properties we will obtain. Handling or normalizing route. Okay, that slow cooling lets carbon diffuse and form layered perlite. Perlite means ferrite plus cementite. Okay, so a typical hypo utentoid steel after normalized looks like a ferrite with perlite. Okay, so it's hard enough for machining, fixed and most sharp brackets and welded structures. If we want ferrite to be strong without losing its characters, we rely on grain refinement, solid solution, or precipitation strengthening in the alloy and cooled working with stress relief when appropriate. Okay, so ferrite is rich structures provide uh, stiffness and dimensional stability. They are two opposite end of the dial-form hardened martensitic structures. Okay, so when we consider about the martensit, it's a forms when we quench austenite fast enough that carbon can't diffuse out. The lattice shears into VCT, a strained. VCT means body centered uh, tetragonal. Okay, so supersaturated structure that blocks dislocation motion. So hardness should up. Okay, so that's why quenched tools, dies, and wear surface feel glass hard. But raw martensite is also brittle and stressed. So we temper to reheat below the critical temperature to let carbon redistribute, relax stresses, and trade a little hardness for a lot of toughness. Lowering the temperature sets the balance and it's maintain maximum hardness, and high tempering increase impact resistance and fatigue life. Okay, so the heat treatment is strength steel, but steel by engineering its microstructure. It very quickly in oil or water or even high pressure gas. That fast cool locks the structure into martensite, martensite, which is very hard but also quite brittle. So we almost always temper afterward, reheat to a moderate temperature to trade a little hardness for much better toughness and stability. Okay, so there are useful variations. Case hardening adds carbon or nitrogen at the surface first. So you end up with a hardware resistant skin or a tough core preferred for gear and shaft. Okay, so induction hardening skips chemistry changes and uses electromagnetic coils to heat just the surface quickly, then quench it, giving you a hardened outer layer with minimal distortion. Okay. Okay, so there is an introduction about the hardening. Okay, so let's summarize the details. So hardening, also we call as a martensitic or quench hardening, is a heat treat route. So we used to make steel very hard and strong. Okay, so we do 3 steps. First one is uh, austenize and quench and temper. In austenize, it's heat the steel high enough so its structure becomes austenite. Okay, so then quench. In the quench, we cool it very fast. Uh, as a medium, we can use oil, water, or gas. So the austenite turns into martensite. That's the super hard phase. Okay, then the final stage is temper. Temper means reheat to a moderate temperature to reduce brittleness and set the final balance of hardness and toughness. Okay, so Why we do these things? Because only hardening gives the combo of high hardness, wear resistant, good hot strength, and workable machinability after temper. Okay, so and for martensitic stainless steel, you actually get maximum Celsius. The internal structure changes to uh, austenite. Okay, think of this as getting the steel into a ready to harden state. Okay, then in the second stage is soak mean hold. Once we reach the target temperature, we hold it there for a short time. That does two things. It lets the wool part reach the same temperature, and it lets the entire structure fully become austenite. During this, the metal specific volume adjusts a normal part of the phase change. Okay, then the third step is quench. Okay, so now we cool it fast, drop it straight from that austenizing temperature into a cooled medium. Uh, Temperature into a cooled medium. The medium can be oil, water, polymer, or gas. So this rapid cool is the quench. It locks the structure into a very hard phase. Okay, so which we will usually temper afterward to reduce brittleness. Okay, so please give me 2 minutes. Okay, sorry for that. I think I'm audible for you. Am I audible for you?
Yes, ma'am.
Okay. Okay. Then the application and materials of hardening. Okay, so when we discuss about the actually use hardening in real life, first it's for heavy duty parts that see big loads or uh, repeated shocks. Think drive shaft, carrier bars, machine frames, forklift forks, lifting eyes, and even nuts and bolts. Okay, so we harden these so the surface resists wear while the core stays strong. Okay, so the hot service parts, anything uh, that has to hold strength at elevated. Okay, so then we talk about temperatures. The hardening helps them keep their shape when they are hot. Okay, then uh, the springs of any size like coil springs, leaf spring, clip, absolutely need hardening and then tempering so they are strong and springy without taking a permanent bend. Okay, so when we discuss about the tools and dies, these things are classic cutting, punches, chisels, rolling tools, plus temper, uh, hammering, casting, and extrusion dies. Okay, so these live by their surface. Hardening gives them by hardware resistant skin they need. Okay, and when discussed about the stainless steel, many martensitic stainless steels reach their best corrosion resistance only after hardening and tempering, which is why it's standard in food and medical hardware. And when we consider about the materials, mainly carbon and alloy steel with enough hardenability to form martensite for a hard surface with a tough core. We choose case hardening. Sorry for that. Sorry for that. Okay, so yeah, we discuss about the double hardening. So this process involves two hardening cycle to create extremely hard wear resistant surface while maintaining core toughness. In common in high stress parts like gear, using methods like carburizing followed by a quench or deep layer hardening plus a DLC coating for materials like titanium, as seen in G-Shock watches. Okay, so it refines grain structure, control case depth, and provides superior strength and durability beyond single hardening methods, often involving mild initial treatments to refine grains before a final severe hardening quench. Okay, so the difference in hardening is a single heat treatment to make steel hard and strong, while double hardening is a more intensive process, especially for case hardened parts involving two heating and quenching cycles to refine the core grain size and microstructure, resulting in a tough core with extremely hard surface. Okay, so that is the difference between hardening and double hardening. Okay, so yeah. Okay, so between those steps, we can add an intermediate anneal around 600 to 650 Celsius with longer hold and slow cool. The goal is to precipitate excess carbon from over enriched austenite, so we avoid retain austenite in the final case structure and reduce distortion. In production, that translates to fewer size uh, corrections after grinding and better gear tooth contact pattern. If you have ever chased size on a deep case gear, you know how valuable that stability is. Okay. Okay. So in this image is a schematic illustration of the complex uh, hierarchical microstructure found in tempered synthetic steel, commonly used in application are silver, oil, are uh, general, and salts can be tuned, and polymer quenchment sits between water and oil. The art is picking a medium that's fast enough to reach martenstite, but not so fast that you crack or distort the part. As example, a thin knife blade might handle an oil quench, while a thick die blocks might prefer a polymer or interrupt quench to limit in a thermal gradient. Okay. Okay. Then after heat this steel, we quenched it. Quench it means cool it fast. So we can drop it into water, brine, or mold, or oil, or just below air or gas. Some shops also use polymer solution or caustic bath. So each liquid or gas pulls heat away at a different speed because they have different abilities to carry heat, store heat, and uh, make loss vapor. So water and brine are usually very fast. Oil is moderated, and air and gas is very slow. And the polymers can be tuned in between. Okay, then the part shape and size matter to cooling depends on surface area relative to the thickness and volume. Okay, so there is a two things, thin part and thick blocks. So when we consider about the thin parts, there is a big surface and small thickness. It's get more, it's very fast to cool. And when we consider about the thick blocks cool slower, even if the surface area looks similar. Okay, as an example, a thin plate harden quickly, and a thick plate cools slowly and needs more severe quenchant or different process to reach the same hardness without cracking. Okay. Okay, so when we quench a hot part, we choose the liquid based on how fast we want to cool. Okay, so oil cools slower than water. That's useful when we uh, want to reduce cracking or distortion. And water cools very fast, but it's harsher on the part. When quenching in any liquid, don't just drop the part in and walk away. You must mix the liquid around the part, okay? Because a hot surface make a steam blanket that illustrates the metal and slows or unevenly cools it. General agitation sweeps away the steam, keeps fresh liquid touching the surface, and gives a more uniform, reliable quench. Okay, so uh, beside besides the water and oil, we can quench it polymer solution. Okay, so these work for steel and also for many non-ferrous alloys like aluminium bronzes. Okay, in terms of cooling speed, polymer sits between water and the nice part is we can tune the speed by changing the polymer concentration. Okay, the common types you will hear are these things. So PVA, PAG, PVP, and PEOX. Okay, so when we consider about why we use them, there are three matters. Okay, so first one is these things more consistent hardness, and it's safer and cleaner. And the next one is they